Good afternoon. I'm Dinesh Minocha from CSEC. Welcome to the MRC Colloquium. So, distinguished speaker today is Professor Gaurav Sukhatme from USC. So, before I introduce the robotics thing, I tell you I've known Gaurav for 30 years, and there's an interesting story. When I first met him in mid-90s, he was a graduate student at USC. Then I met him in late 90s. He was a research faculty at USC. Then I met him a few years. He was like a tenure track faculty. Then I met him a few years, he was a department chair. And now I've met him, he's a director of advanced computing and a vice dean. What will he be in 3 years? You can all extrapolate. So he doesn't know the answer.
Maybe the president of
And the current president is stepping down. That's coincidence. Okay. But anyway, Gaurav is here today. Of course, he's an administrator, but you think, besides administrator, he's a great robotic researcher. He's very well known in the robotics community. Did a lot of work on network robotics, field robotics, robot learning, distributed system. He's a director of the USC Robotics Research Lab. As probably you know, USC is one of the strongest research groups, as well as robotic embedded system director. He is extensively published, very well cited. He's a fellow of AAAI, AAAS, IEEE OCA Foundation. And besides doing administrative job at USC and a big robotics group, he's also a Amazon scholar. And he think he was getting too much sleep. So to compensate for that, he's been pioneer of many big robotic conferences. Like, we all publish in RSS. He's one of the founding members of that 2 decades ago, and editors a lot of journals. So I think his resume is too big for me to cover, but let's welcome to UMD and hear about how to get robotics with 20 neurons.
All right.
Thank you.
All right. Thank you so much, Dinesh, for inviting me and also for the very kind introduction, and thank you all for coming, especially on a rainy day. So as Dinesh said, I'd like to tell you a little bit today about this line of work that we've been doing in my lab on learning minimal models for control. And we'll pick a particular problem that people in the multi-robot community have an interest in and see how far we can push some modern learning-based approaches for it. And perhaps more interestingly, if there are some lessons to be learned from this story. So all of the experiments I'll describe in the talk today are centered around this one platform. Some of you probably have played with this platform or worked with this platform. This is a very small quadrotor. It's called the Crazy Fly. And it's less than 30 grams. It has one CPU on it, no GPU. It has a tiny amount of RAM, and the important thing to remember is that RAM is in kilobytes, not in megabytes, right, or gigabytes. And it stays in the air for 5 minutes, 5 to 10 minutes. It's a good experimental substrate, but it's a very minimal system, right? This is all you have. It does have a fairly decent IMU though, and it's clocked pretty quickly. So you can clock this thing up to about 500 hertz, right? So this is the platform. I'm going to show you a sequence of results on this and tell you a little bit about our experiments with this. So way back, about 7 or 8 years ago, in collaboration with Nora Anyan's group, who was then at USC, we spent some time thinking about how to coordinate very large-scale robot teams. So these are 50 robots that we want to fly in under some designated conditions. So they begin at some start locations. We want them to end up at some designated end locations. There's a set of obstacles in the way. And this was largely in those days, at least from our perspective, we conceived this as a planning and online replanning problem. So we would build sort of these tubes that allowed robots to reason about collision-free areas and then progressively refine their estimates as they were flying through space. And we were able to do this in a way that was computationally efficient. And this was a line of work that was published in a sequence of papers that are listed here. There was no learning in this. And the assumption was that the positions of the obstacles were known in advance, that there was some mapping system that had already told you where the obstacles were. And there's some discrete planning on a graph and then some refinements using a couple of solvers and so on. But my talk today is not about this. My talk is sort of just to use this as a point of departure on how we thought about these kinds of multi-robot coordination problems a few years ago. Now, having sort of played with this, the question my students and I asked ourselves was, is it possible to do essentially the same task, but is it possible to learn controllers for robots to do this task? So the learning problem would be that robots start in some location, they are told to go to some location, and the control signals on each robot would be generated not as a result of a planner putting output, but as a result of a learned system. Right? And the idea is that the robots shouldn't collide with each other, they shouldn't collide with obstacles in the environment, same as the planning problem I showed you. They should end up at the goal locations designated to them, and so on, right? And as is usual in these talks, the answer is yes, you can do this, and I will show you. I will show you today that you can in fact do this, right? But more interestingly, there are some lessons to be learned, I think, from it. Now we set ourselves some constraints. This is not a completely unconstrained learning problem, and some of these constraints are induced by us as experimenters. They're not necessarily the only framing of the problem. So my particular interest was, can you do this with reinforcement learning in particular? Right? So this is a choice. It is not necessarily the only way to learn such a controller. But for certain reasons that will become clear later in this talk, I was interested in asking the question, can you do this with reinforcement learning? And deep reinforcement learning in the sense that can you train a neural network using reinforcement learning? Right? We also had in mind that the learned controller would put out actual thrusts to the 4 motors on each vehicle. And so the idea was to really learn a output that was directly usable on the vehicle in some sense, right? So that was another one. You can learn other things. You can learn something about controlling an abstraction of the system, like its center of mass and has sort of some point dynamics that you want to move around and things like that. But we were interested in really learning, so what should the 4 thrust vectors do? And the reason we're interested in this is because we thought that if we were successful, then potentially some of the maneuvers the vehicles would execute under this may end up being more agile or may end up being somehow different or better than the types of things we were pre-programming earlier. Right? But we were also aware that in order to do this, we would have to face a gap between the system we wanted to implement on and very likely the system we were going to train on, which would almost certainly be a simulator of some kind. Right? So this was our setting. So our first cut at this happened in 2019, about 5 years ago, where we focused on only one robot. So there's no multi-robot problem here. And there's only one goal, which is that the vehicle is expected to hover stably at a given location in space. So this is a restricted version of the problem. So you have a vehicle, all you want to do is to hover, and you want to reject sort of wild disturbances, which are what you're seeing in the video. And the question was, could you learn using reinforcement learning a controller that could stabilize the vehicle at a location in space, bring it back to that location in space after being subjected to all kinds of disturbances, and also could you do this for a family of vehicles? And the family of vehicles we had in mind were quadrotors that were all in this X-cross configuration. So the Crazy Fly on up, we had 3 such vehicles, right? So broadly had a similar configuration, 4 thrust vectors on each one, but fairly different dynamics in the sense that their masses and inertias and so on were quite different, right? And there was really, this paper really had only one sort of, what at the time was not also maybe such a secret sauce, but if there was a secret sauce, it was just domain randomization. So with fairly basic reinforcement learning, just implementing PPO, we were able to do this. And we got fairly agile control, fairly smooth trajectories, and we were able to show that you can actually do this on multiple platforms, right?
Does this have any perception?
This has all Vicon only. So no perception, only Vicon. Yeah. So yeah. And there are no obstacles here. There's only one robot, right? All you do is go hover. Right? I disturb you, go back and hover. Right? That's the only time.
So here the displacement is happening because that person
is
physically...
Yeah. Just disturbing it violently.
The bad guy in the room.
Yeah, the bad guy. Yeah. So this received some attention when it was published, but it's basically the controller, the learned controller that we're going to build on for the multi-robot version of the problem that I'm interested in here today. Right? Okay, so today is about multiple vehicles. We care about collision avoidance, both with vehicle-vehicle collisions as well as with the environment, right? Particularly, we want to do this with direct thrust control. We want to show that it actually scales to reasonably sized robot groups, right? A few tens of robots at least. And most interestingly, we'd like to be able to show that this, in some sense, generalizes. One of the annoying things about my first video was that you sort of have to know where the obstacles are, or you have to have some online mapping strategy that's fairly good at building maps that you can then plan with. The question here we're going to ask is, what if all you can do is measure, and we're going to measure ranging to obstacles, then can you still navigate to your goal and do obstacle avoidance without having to build full maps, right? And we'll show that this is possible. So this paper appeared a couple of years ago in Coral, which is going to be the sort of 80% of my talk is about this paper, and then I'll talk a little bit at the end on follow-on things that we've done. So the basic formulation is absolutely simple. Each quadrotor in the environment views the other quadrotor simply as part of the environment, right? And this is the classic picture from Sutton and Bartow. And so there are several things that go into the state. So I'll just describe the state. I'll tell you how the reward is structured. I'll tell you a little bit about the training, and then I'll show you some results. And so each quadrotor measures the relative position between itself and the goal that it's currently designated to go to. In the first set of experiments I'll show you here, these are available through Vicon, but we have since then relaxed it, and we actually do visual odometry in order to keep track of position, albeit in a constrained indoor space. Each vehicle also has access to its own velocity vector. It has access to its attitude, a rotation matrix. It has access to its angular speed. These are all measured on board using an IMU. And each vehicle has access to the relative position and the relative velocity between itself and its k closest neighbors, right? And k is a choice. K is a so-called hyperparameter, right? And the experimenter picks what k is. So keep this number k in mind, because if you have n vehicles in the system and k is roughly as big as n, then that's kind of not a particularly interesting result. So a good scaling result would be as n grows big, k grows either logarithmically or at least sublinearly in n, right? Otherwise, there's really no multi-robot angle to this. So I'll say a little bit about, at the end of the talk, about why we think we have some good results on relatively small values of k. Right? So that's one thing to keep in mind. There are 4 outputs on each vehicle because there are 4 actions. There are 4 thrusts to 4 propellers.
So what are the k nearest neighbors? Is that coming from a central server, or you track?
Yeah, so in our first round of experiments that I'll show you, all position data is available to a central system through Vicon, and then we selectively hide from each vehicle the ones that are non in the k set. And so it's told which one. Yeah. And so it's sort of mimicking what would be the reality. Okay. Right. And so now we need some sort of simulator in which to train. Right? And one of the things that I'm going to show you today is all training is going to happen in simulation. So we will not fly even once on the real vehicle in order to gather data. We will train only in simulation and then transfer, and I think the modern terminology is transfer zero shot to the real vehicle. Okay? And so our simulator is very simple. It's the basic dynamic model of a quadrotor. This is sort of 101 textbook model of the quadrotor, right? Implemented in a custom simulator that we wrote. There are some tricks with the simulator. If you're interested, it's written to be optimized in ways so that it runs fast, and it's really useful for RL training. So if you're interested about it, ask me after the talk, and I'll point you to it. You can download it. It's free. You can play with it, right? It's just a nice software artifact that you can do things with. And the RL pipeline is fully integrated with it if you want that. But the interesting part here is not the dynamics of the helicopter. The interesting part is, what do you do when things collide in the simulation? And so we have in the simulator what I'm going to call a simple randomized collision model. And this is something that became more important than I thought when we began the project. So our collision model goes as follows. We have no idea what complex machines like this do when they collide, and we have really no hope of modeling it. So one thought was, well, let's model them as idealized spheres and model some sort of semi-elastic or inelastic collision of some type, or even a perfect elastic collision of some type. That's a reasonable thing to do. They actually tried that, and for reasons that will become clearer later today, it is in fact not the right thing to do. So in fact, what we do is we randomize collisions. So when 2 vehicles collide in our simulator, their velocity vectors are set on 2 sides of opposing half planes in random directions. it is not at all a model of what actually happens. It's just a model that allows the simulator to continue simulating, right? So this is an odd choice to make because it's not an idealization of a thing, nor is it some attempt to actually capture the physics of a collision, but it's some entirely different thing, right? And it turns out to have immense value in simulators like this. And I'll come back to why I believe this is true. And you might be able to extract some mileage about, from a choice like this in other settings as well. Right? So just keep that in mind. So there are two things I want you to keep in mind. One is whether the system really scales. In other words, whether these neighborhoods really need to be super big. So pay attention to that number K. And the other is, what is the role of this randomized collision model, and did it really bias anything? And I'll have something to say about both these things. Right? The rest of the stuff is fairly orthodox.
Just a stupid question, maybe.
Yeah.
When you say randomized collision, is there any dynamics with that collision?
No. So when the collision happens, we basically transport the states of those two vehicles to the same position where they had collision, but their velocity vectors are magically transformed to velocity vectors that are on two sides of a plane that divides them. And the directions of those two vectors are picked uniformly randomly from 0 to 180 on either side of that plane. That's it.
So there's no forces? Or
No, nothing. We model no forces. There's no coefficient of restitution that you can tune, so nothing, right? It also has the added value that there are essentially no parameters to tune in that model. There's no other degrees of freedom that are sort of secretly need tuning, right? You sort of give up all control, right?
So typically, people would model this as like, there's a ball around me, and as you enter my ball, I will start reacting to it.
Yeah.
And that would be maybe how you react.
We're not going to do that. We're not going to do that, but we're going to do something like it because I haven't told you what the reward function is.
Okay.
So how do you penalize collisions is the other piece of the story, and that we'll do that there. But we're not going to do it in the simulator. In the simulator, when things collide, we'll just reset the state to this new imagined state, post-collision state. Right? It's random, but it's not like those two vehicles are transported to some random part of the world. It's a sort of a zeroth order model of a collision, not a first order model, right? So that's what it is. Now we need some training environments in order to train. And so what we do here is we basically uniformly sample from a geometric pool of shapes. So we've got a bunch of shapes that I've shown you here, like each dot is a goal. So the blue robot has to go to the blue dot, and the red robot has to go to the red dot, and the yellow robot has to go to the yellow dot, right? And so we cook up a bunch of shapes like this, we dilate them, we expand them, we stretch them, and we cycle the simulator through these. These are where the vehicles are trying to fly in the simulation, right?
For some of these shapes, you may have analytical solutions to those equations.
Yeah, you may, but remember the thing I'm interested in is flying to these things when there are going to be obstacles that pop up.
Yeah.
And so in some sense, I'm not too invested in like trying to figure out the shortest path to the goal or any such thing, right? Because then I need to start planning. And right now, I'm just going to pretend that I'm going to train in environments in the beginning where there are no obstacles, and I'm going to show you how to do it with obstacles. But yeah, right? And so we change these positions, the geometric shapes of the goal after some random periods of time in the simulator. The details are in the paper, exactly how we do this. And then there's some variants here where we do some crazy things, like robots are told to go to certain goals, and then their goals are swapped, so the robots are sort of have to fly through each other. So you exercise the simulator in ways that sort of cause the robots to be put into states that you might expect to see in reality, and hopefully the controller converges to a set of learned parameters that allows them to exhibit the kind of behavior you expect to see in reality. This is roughly the training regimen. There are some details in sort of how frequently you cycle through these shapes, how you change them, how, et cetera, and so on and so forth, but I'm sort of skipping over those here, right? So these are sort of the set of training environments. So there's a simulator that essentially mimics essentially enacts a set of dynamics that drives a system. The system is trained on a variety of sort of goal-achieving behaviors. Now you have to penalize the system or reward the system in certain ways in order for your reinforcement learning to work. So I should tell you something about the reward design, right? And so the reward design is relatively simple. You have good reward for achieving the goal. So you want the vehicle to actually get to the goal. So not surprisingly, you take the two norm of the position separation between the vehicle and the goal. So that's fairly simple. there's a hefty penalty for a collision. So we don't want collision. Seems very reasonable. There is a gentle penalty for being very close to your k-nearest neighbors. So this is what you were alluding to earlier, right? So you don't want a delayed reward situation where the only reward is, or the only penalty is when you collide, but you sort of want something that penalizes you if you get too close. It turns out you need both. The last three pieces really are inherited from the single quadrotor version of the problem. So the video I showed you where my student Artem was, kicking the robot and moving it around, which was just a stabilization problem, the reward function for that is really maintain a stable attitude, don't have dramatic accelerations, and stay upright, and are the three terms. Right? And so the new reward function adds a collision penalty and a reward for reaching an arbitrary goal G. Right? That's the structure. So now, in terms of how we train, so this is sort of, from an RL perspective, about the simplest thing you can do. We basically enact a version of PPO in order to do this, where we're maximizing the expected sum of rewards, discounted rewards of the structure that I've shown you. And we have two model architectures that I want to sort of tell you a little bit about, and then tell you why we made some choices about the structure we picked, right? And so the first structure that we picked that I want you to look at is this sort of deep sets architecture, which has a mean operation in it. And so on the upper left are the self-observations. So each vehicle is observing its own state and is trying to minimize the distance between its own current position and the position of the goal that it's commanded to go to. We put those self-observations on each vehicle through a MLP, right? This is small MLP, right? And the output of that is then combined with the encoding of the neighbor observations. So the neighbor observations are the k nearest neighbors for each vehicle. These are reshaped to k pairs of neighbor observations, right? These are put through, and you generate k latent vectors for k pairs of neighbor observations, and you take their mean, right? So this is because you want some permutation invariance. You don't really care what order you see your neighbors in. And so the simplest sort of way of doing this is this technique, right? It's not the only way of doing it, but it's a simple way of doing it. These two are summed. These two latent representations are summed, put into another MLP. So all the neural networks here are very small MLPs. And at the end of the talk, I'll tell you just how small, right? But I think you know from my title, how small, right? And the task of that last MLP is just to generate 4 numbers for each vehicle. And a copy of this controller is going to run on each vehicle, right? And so you can see why the small business becomes important, right? In the end, my forward pass is going to be through a system that needs to be small if I have to have any hope of actually running it on the vehicle. Right? So that's the overall structure. Now,
Gaurav,
yeah.
Are you going to tell us where you're going to exploit the permutation invariance?
Yeah, I'm going to tell you in a second. I'm going to tell you, in fact, that it's not the best idea. You may have guessed why. In fact, ordering of your neighbors does matter, right? Because if you have 3 neighbors near you, but one of them is hurtling towards you at high speed, they're actually more important than the other 2. So in fact, you probably don't want to do this permutation invariant thing. You probably want to do something different. And most of you can probably guess what that thing is. You want some attention mechanism. You want to attend to some of your neighbors at priority, right? So this becomes effectively a baseline, right? So if you looked at all k of your neighbors, pretending that they were all the same, is sort of one way of doing it. But in fact, I'll show you that there's a slightly better way of doing it, right?
Does it give you some robustness with respect to individual failures? Since
Yeah, it does. It does, actually. In fact, the extreme version of the system that I'm going to show you in flight pays attention to only 2 neighbors. And so there it's really not, it's moot what you do. But if you sort of, most of our simulation runs are with 6 neighbors at a time, and there it gives you some robustness if you get to drop out and occasionally you don't get good data from one of them and things like that. There's some value to it. But yeah. So the other way of doing this is to build some sort of an attention mechanism to convey the relative importance of different neighbors, right? And so the way we do this is the self-observations are treated the same way. Each vehicle encodes its own state, or rather more precisely, the delta between its own state and the goal state the same way as before. But now the neighbor observations, they're reshaped to these k pairs of observations. You generate k latents for these k pairs, but now you generate k attention scores for them. Right? So this might be the world's smallest attention mechanism implemented in a few kilobytes on these small vehicles. Right? And then the output is again summed with the latent observation, the latent representation of the self-observation, and sent to the same MLP as before to generate actions. Right? So this is the second architecture. So let's look at some results and let's go back and think a little bit about whether this actually makes a difference or not. And let's play with some of the parameters now, because there have some choices that have been made here in building this up. So there are three graphs on this slide. Right? On the x-axis in all three, this is all training time, right? So this is all what is happening in simulation while we're training. So on the x-axis are the simulation steps. We train for 1 billion steps. Right? So that's the x-axis. On the figure on the extreme left shows the average reward per episode on the y-axis. The figure in the middle shows the average distance to the target as a function of simulation steps. And the figure on the extreme right shows how long, what fraction of the episode do the vehicles stay in the air. So remember, when the simulation begins, the vehicles don't even know how to fly. So in the beginning, as you can see in the picture on the extreme right, they hardly spend any time in the air. They mostly generate control signals that sort of just cause them to do crazy things on the floor. And then after some time, they learn to fly, and the fraction of time they spent in flight increases. And that sort of tails off at some point, because occasionally a collide fall out of the sky and so on, right? So that's all the picture on the right is showing. The picture in the middle shows the average distance to the target. And in the beginning, there's no notion of actually getting to the target. The vehicles don't even really fly. But over time, that distance tails off. It doesn't quite ever end up at zero, because we do some crazy things like tell two vehicles to go to the same target. So in fact, it's not achievable to fly to the same target. There's also some error that the controller is not able to zero out. But you get some sort of asymptotically good behavior and approach to target. And then on the leftmost picture is the picture that every RL person has to show, that these things are good at gaining reward. I've always found that picture to be particularly meaningless, because just gaining reward doesn't mean anything. I care about whether the behavior I want is actually the behavior I expected. But yes, of course, they're good at generating reward, at gaining reward. So now the question is, can you draw any conclusions from this for the 4 controllers that are shown on each of these panels, right? So one of the controllers is so-called a blind controller, right? So this is a controller where the vehicles have no access to their neighbor states. As far as each vehicle is concerned, there are no neighbors, right? So that's one, and that's the one labeled blind, and it's the dotted line. There's one that's called just MLP, where all we do is we pass the inputs through an MLP and try and learn whether we can generate control signals from them. And then the other two are these sort of deep sets and attention mechanisms, where these encoded latents that are combined to generate the output. In one case, in this permutation invariant way, in the other case, with this attention mechanism. And if you look at it, you might think sort of, if you look at the middle graph in particular, which is the distance to target, I mean, it's fairly clear that the blind system is not great, but that's not surprising. That's okay. But it's not super clear that there's much to choose between the attention mechanism or the sort of deep sets of mechanism, or just having an MLP do the task. Collisions are fairly rare. I mean, we end up with about 20 collisions over 1 million training steps, right? This is all in simulation, by the way.
But that also depends on the density,
Yeah.
Distribution.
Yeah. So as Dinesh correctly pointed out, results like that mask what is actually happening, right? What you really should ask is pick some of your challenging tasks. Like, so for example, now look at the central panel, measures the average collisions for the pursuit-evasion task, where in fact there are, if you don't learn to fly well, you're likely to collide more frequently. And the picture on the extreme right is the average collisions for a task which in the paper is labeled sort of this static same goal task, where you have a lot of robots, but they're all told to fly to the same location. So it's a collision-inducing task, right? Where things approach each other, they approach sort of in close proximity. Now what you can see is, of course, the blind controller doesn't do well at all. But again, that's not a big surprise. But you can see now that the attention mechanism is actually measurably better than the deep sets mechanism. Yeah.
Pursuit evasion, is collision a bad thing?
No, we tell two pursuers to follow the same target. So the two pursuers collide with each other.
So this is measuring
Yeah.
only pursuer.
Well,
collision,
we
not-
measure any collisions, but you generate these things where some collision is more likely to happen. Yeah, so that's how you generate collisions. That's how you kind of create sort of a situation where more collisions are likely to happen.
Normally in a pursuit evasion,
Yeah.
you want the
Collision is
pursuer
great.
to collide
Yeah,
with the evader.
Yeah, absolutely, right? So yeah, I mean, there's some evidence, there's some numbers in the paper that actually do some statistics on this, but such attention mechanisms have a role, and they have a role where it matters, right? If the task is easy, maybe they don't care so much, but where the task is difficult, there's actually some benefit. This is something to keep in mind. And actually, interestingly, because these networks are very small, you can actually see it in the attention weights, right? You can see in the attention weights that if you look at the blue quadrotor, for example, you can see that the relative importance of the red one should be sort of higher than the gray one, given how they're flying. And the relative importance of the gray one should be higher than the importance for the green one, just based on how I've set it up. You can see that in the attention weight, darker weights are higher attention, right? And that's exactly what you expect an attention mechanism to do, right? So closely located, fast-moving neighbors, you attend to more than the ones that are not. I'm going to resist making too many biological analogies here. This is not a paper that is faithful to the biology in any way, so don't take it like that. But you start to see that with small systems, parsimoniously choosing some architectures like this, you quickly end up paying attention to the things that matter just for the task you care about. And here, there are only two things that matter. Navigate to the goal and don't collide. That's it. That's the whole task, right? And the question is, to do that, you need very little, right? You need very little. And this sort of bears that out, right? So let me show you a couple of other things now. So now let's look a little bit at the scaling business, okay? So this picture has the number of robots on the x-axis, and on the y-axis is a measure, which is the number of collisions, but I've normalized it. So it's the number of collisions divided by how long the episode lasts in minutes times how many robots there actually were in the episode. So all our experiments happen in a closed enclosure, so the volume is constrained, right? So they can't fly away to infinity. So now, the reason I normalize by how long the episode lasts is because, if you fly for a very short period of time, I might be able to report there are no collisions, but in fact, to fairly compare a 4-minute episode with an 8-minute episode, I need some normalizer. So that's one. And the second is, obviously, if I'm flying around and there's no other robots in the environment, well, then I can have some very nice collision-free results. But in that same 10 by 10 by 10 environment, if there are 10 other robots flying around, then I need some fair way to compare. So that's why I'm dividing by those two numbers, right? So it's the number of collisions is on the y-axis, but normalized in this way. On the x-axis is just how many robots there are, okay? Now, first, I'm going to have a system where there are 8 robots in the environment, and I'm going to pick a neighborhood size, which is very generous. I'm going to pick 6 nearest neighbors. So that's very large, right? Because if you have a system with 8 things and you choose to call 6 of them neighbors, then you're only ignoring 1 robot. So K is pretty large compared to N, right? This is the so-called 8-6 configuration. But I'm going to train on this configuration, right? I'm just going to see what happens. If I train on this configuration, I converge to a set of learned weights. Then I'm going to test it with n equal to 8, and I'm going to test it with n equal to 16. But I'm not going to retrain for n equal to 16. I'm just going to run the 8-6 controller on n equal to 16. And then I'm going to test on n equal to 32, 48, 64, and 128, right? So that's the graph that says pre-trained, which is the star, right? And it's the dashed line, right? So not surprisingly, for n equal to 8, it works really well. It was trained for 8. And what's more is it was trained for 8 with a very generous number of neighbors. So very few collisions, right? But then if I run that same controller on 16 robots, you get somewhat more collisions, but not unreasonable, right? But things start to go really bad if you run that controller with 32 robots. As you can see, the number of collisions jumps by a factor of 4, nearly 5, right? And then it's completely hopeless for n values greater than that. So if you take this system and you train with a neighborhood size of some fixed amount with a small number of robots, you can't just run that controller on larger and larger numbers of robots. It breaks fairly quickly.
What does fine-tuning mean?
I'll tell you in a second. Yeah. So the second controller is this sort of so-called pre-trained plus fine-tuned controller. So pre-trained plus fine-tuned means the following. I train on 8.6 for 1 billion steps, right? And I have this controller. Now I allow myself 200 million more steps of training, but this time, instead of doing 8.6, I'll do 16.6. So I'll keep 6 the same. You still pay attention to only 6 neighbors, but I'll allow you to train in a 16.6 training environment. That's my fine-tuning step. And I do 20% more training in the fine-tuning step. Okay? So now it turns out, and that's the solid line with the filled circles in it. And you can see that the performance of that is actually quite good, right? It's not limitlessly good, but it'll give me scaling out from 8 to a network of robots that's nearly 8 times that, since there's 64 robots. At 128 robots, things are not that great, right? You can see it sort of goes up at the end. And then, of course, what you can do is you can measure against just retraining from scratch every time. So you train a controller for 8.6, you train a controller for 16.6, fully from scratch, retrained all the way from the beginning, for 32, for 48, for 64, and that's the blue line, right? And that ultimately will be better than anything else, except you have to retrain from scratch every time. Yeah.
Is there a particular reason that you select from A6? Why don't you select like 4.3, something like that?
Yeah. The 6 actually is a reasonable, there's some effort we put into 6. There's actually some work in the literature that suggests that when you do collision avoidance in tight spaces, in the biological literature, that small flying animals tend to pay attention to 6 of their closest neighbors. We actually looked at everything from 4 to 8 for neighborhood sizes. And looked as in we experimentally swept that, and 6 seemed to be a good number. There is not a whole lot more science I have to say about that, right? That's one. And why did we do with 8 and not with 6? We've done smaller networks as well. We have some results on doing those. And in fact, the real flights that I'll show you on the vehicle, we only attend to 2 neighbors, as it turns out. And it still works in a reasonable fashion. Yeah. There's nothing it's not sacrosanct. Yeah.
But I understand the 6 is, I think it's a good approximation. People look at murmurations.
Yes.
One of the most challenging thing, and even human crowd.
Yeah.
The one thing comes up is, how accurate do you know the neighbor's position?
Yeah.
And velocity, whatever the derivatives you do. So how much it depends on how well you can anticipate how they're moving. That's a big part of collision avoidance.
It's a really good question. And it's perhaps one of the, when Dinesh asked me earlier, how do you know your neighbor's states? Well, when you fly in Vicon, you centrally capture them and then you distribute them selectively. But that still is nowhere close to what you would do in reality if you had a camera on the vehicle that was supposed to track the neighbors. The lags would be different, the accuracy would be different, there would be dropouts, there would be occlusions, there would be all kinds of things that are not mimicked here, right? I don't have a good sensitivity analysis or ablation for that, to sort of say, how sensitive I am to the fidelity of those measurements. And maybe there, having more neighbors than you want, Colleen asked the question earlier, you may just want slightly more neighbors because you'll never have that data as pristinely as you may have it in the simulator. So yeah, it's a good point. It's a good point. Yeah. Yeah, I think I said all this. So let me show you sort of what this looks like. This is how things fly in the simulator with no obstacles right now. So, the robot of a particular color has to fly. This is now not in training. This is the learned controller, right? And this is how you test them. You sort of pick a variety of goal locations where the robots have to fly, right? And so that's fine. I mean, they exhibit, not surprisingly, pretty nice flying behavior, but the physics here are the physics they were trained on. There are no obstacles, so it's not entirely surprising, right? You can ask them to do some crazy things. You can ask 32 of them to fly to the same point in space. This is what they end up doing. It's not an entirely unreasonable output. Some people look at it and use words like emergent behavior to describe it. I'm going to just stay shy of that. This is what they do. I think this is reasonable. Here's what they look like when you deploy them, right? And so here are 8 vehicles. They begin in a 4x2 grid. They're told to fly to a 3x3 grid. Then they're told to fly into a circular formation and then back to a 4x2 grid.
This is real.
Yeah, these are these crazy flies flying around, right? And actually, here we're not even flying an attention mechanism. We're just flying this deep sets mechanism. We're running the IMU at about, we're closing the control loop. This is just a single thread of control that we close at about 100 hertz. There are about 1,600 parameters here. Each MLP has roughly 20 odd neurons in the hidden layer.
So your equations didn't have thrusts or whatever other terms, or did it have?
They did.
They did.
Yeah.
They did.
You put torques into the system and you generate accelerations.
Yeah.
That's the simulator.
Yeah.
And then you integrate the accelerations twice to get the position. That's the simulator, basically.
And so you are able to physically control using that.
Yes. Yeah, that's right. So other than the thrust generator in each vehicle and gravity, there's no other aerodynamics being simulated here at all, right? It's about the simplest. So you're assuming that the blades are rigid, that the torques directly translate to body accelerations and masses in some highly idealized fashion. So yeah, the simulator is about as basic as it gets, right?
No downwash either?
We do not model downwash, but I will have something to say about it, right? So we can deploy this. Empirically it seems to work, right? So now, what happens when they collide? This video is a little hard to see, and I'll keep playing it. So watch what happens when they collide, right? So now here's a collision, and in fact you get a ground collision. They will recover from these collisions, and flight will continue.
How was ground collision modeled there? Or was it?
It's the same way as I showed you.
Was it?
Right. So I showed you some numbers. It's not that collisions don't happen. They do happen. It's not that we want to learn a controller where collisions are okay. We want them to be as few as possible. But our post-collision behavior is often quite interesting in the sense that we're able to actually continue flying. Not always, but quite a bit more frequently than we were able to when we were hand-coding controllers for these vehicles. Right? Now, one of the reasons for that, the hypothesis is that in the simulator in post-collision puts the vehicles into states from which they are forced to learn stabilizing behavior. And it's actually quite handy. It's actually quite a handy thing to have in the real world, right? So it is not important that you model the fact that, it's not important that you model the physics of the collision. It's important to model the fact that there will be a state after the collision. And as long as you are in some envelope of states that look like the post-collision states in reality, you will have control actions that you will have learned that may be useful there. Right? Now, I've waved my hands a lot while saying those words, right? But I think there's some interesting principle here. And the principle is that in some cases in robotics, it is better to have a large sim-to-real gap, but have a simulator that can keep going, rather than try and close the sim-to-real gap and have a simulator that actually is hard to run. Right? So this is a conscious choice of actually making the simulator not be like reality and yet being useful. Right? Now, that's not a prescription for doing everything, and it is not a prescription of how you should learn offline for all of robotics, but there are some cases where this may not be a bad thing to do. Right? So it's just something to keep in mind. Now, the other thing is, this is empirical work. So at a minimum, we should at least compare against people fly vehicles without colliding with each other all the time. I mean, if you took a multi-robot systems class, and you wanted to fly n vehicles from A to B, you would probably implement something like this, right? You could imply like buffered Voronoi cells. Each vehicle has access to the same information my vehicles have access to, which is where the neighbors are. You draw the Voronoi partition, and the safety constraint says that within your Voronoi region, you are relatively a free agent with some bounds on your velocity, and you replan and you recompute the Voronoi regions as you go, and this is a provable technique that doesn't lead to collisions, right? So we should baseline against this. This technique obviously has one thing going for it that our technique doesn't, which is that it is provably guaranteed not to have collisions, whereas the technique I showed you doesn't have that guarantee. But let's look at the performance. So we implement both. On the left is a BVC implementation, on the right is our implementation. Same task, 8 robots, and they're told to swap positions. And you can see what they look like. The one on the left is the BBC implementation. The one on the right is ours. The interesting thing is not so much that it quote unquote works. The interesting thing is what kind of flight modes you generate, right? So if you look, for example, at these two graphs, what you'll see on the left is the BBC controller. On the right is our controller. The upper panel is the velocity. The lower panel is the acceleration. And you can see how in the BBC technique, the flight is more conservative. Our technique, the flight is more aggressive, right? So the flight modes are kind of different. Right? And of course, on the left, it comes with a guarantee that there's no collision. Right? So I don't offer this as A is better than B. I just offer this as a view to sort of, what do you get out of these systems? Right? In our system, you can also do crazy things, right? So like the very first video I showed you in my talk, when you plan, replan, build environmental representations, the system that we've trained is effectively a reactive system. You can lob a beach ball into the system, and as long as neighbor observations are available, right, you can react to things. You don't need to plan or build complicated representations for a task which fundamentally is about not running into stuff and about navigating to stuff, right?
What do you know about the obstacle in this case?
So the same. So the obstacle is an agent whose positions you're able to. So if it is one of your K neighbors, then each quadrotor has no way of knowing that it's in fact an obstacle. It just thinks of it as another entity in the environment to which it is ranging.
And the size?
We know nothing about the size, just know the range. So obstacles can be arbitrarily big or small. There's no such notion in the vehicles, right? You're getting 6 range measurements of 6 things near you that you need to attend to. You attention score them, you pay attention to the one that you weight them based on the ones you care about more, and then you generate a control signal in response to that. That's it. That's the whole controller.
So in principle, if I make the obstacle bigger,
yes,
I would have to fine tune.
Yeah, I'm going to show you that. I'm going to show you that in a second. You anticipated my question. So what about environments with real obstacles, right? What about environments where there are actual real obstacles in the environment, right? But again, with no map in advance, right? So this just appeared at ICRA earlier this year. So I'm going to go through this at much higher speed because I think I'm going to run out of time shortly. So again, here, n quadrotors in the environment, but a bunch of static obstacles. Let me start with the technique is not much different. I'll just tell you what's different about it in a second. Let's flip through this. Yeah, so now our obstacle observations are a little bit different. We were taking the norm of the distance between the vehicle's position and its K nearest neighbors. We've now switched in our newest implementation to an SDF, is how we measure the obstacles. And we have a multi-head attention module instead of separate attention modules. I'll show you that in a second. So the multi-head attention module works as follows. This attention module is going to prioritize between observations of flying neighbors and observations of static obstacles. So in some sense, if you have a static obstacle which is very nearby and your relative speed to it is high, you want it to have higher priority. But if it is very nearby, but you're already flying away from it, you can essentially ignore it, right?
So different heads for each of these?
There's one multi-head attention module. But it produces 2 encoded representations. So we produce 3 latents. One is for the self-encoder, one is for the neighbor observations, and one is for the obstacles. We concatenate this into a single latent and decode using 1% NLP to generate actions. It's a slightly different than what I showed you before.
Gaurav, my experience that generally dealing with a static example is
Yeah.
dynamic obstacles are harder to handle.
Yeah.
If a big dynamic is coming close to you, you can
Yeah.
dynamically get the attention to.
Yes, and so it'll receive much higher attention scores. Yeah. The other thing we do is this trick, which comes really in handy, is this using a replay buffer, where you want to amplify collision events and sort of enhance collision aversion. So you maintain a replay buffer of the states that lead up to a collision, and you essentially replay these states in the simulator more frequently until you've seen them for a certain amount of time, which is a parameter, and then you drop them from the buffer, right? So it just sort of amplifies these, and so you quickly learn. You want to quickly learn two things. You want to quickly learn how to fly stably, and you want to quickly learn not to run into stuff. If you can do these two things, then you can fly to locations and do sort of goal-achieving behavior, right? Now the knock on this work is people are, the question I often get is people say, well, but look, you already know how to write a controller for flight. Why not begin there? Why begin to learn from scratch? And that's a completely valid point. It's mostly because we wanted to see how far we could push this. It is not a practical way to do things. Like if I had to do this in reality, I would learn with a stable controller and then maybe learn aggressive maneuvers on top of that, right? So I want to draw a distinction between sort of launching an exploration to see how far it could take us and a utility measure for what you would really do, right? So I want to draw that distinction. It's an important one. Yeah. So anyway, we have done a bunch of ablations. We've removed things like this multi-head attention module. We've done things like remove the replay buffer, and these things do matter. So if you want, you can look at the paper. You'll see that each of these things give you a little bump in the performance. And then in this environment, you can also do things like compare to techniques that exist with, for example, with safety barrier certificates, right? So what about techniques that give you guarantees when there are obstacles? How well do you do, right? So what you'll notice with us is that our system is more live in the sense we will always fly. We are not guaranteed we're not guaranteed to avoid all collisions, but if you just measure goal-achieving behavior, as you increase the obstacle density, conservative techniques that cannot find safe paths will not achieve goals. They will never collide, but they will also never reach the goal, whereas our technique will collide, but our goal-achieving percentage rate of success is high. Why is this useful? It's useful in peculiar settings. If you're in a post-earthquake scenario where there's a lot of rubble and you want to send 100 crazy flies in, it doesn't matter if 3 or 4 of them die. That is not the time to run safety barrier certificates and say, well, I couldn't reach the goal because there's a narrow passageway. That is the time to actually try to fly through that narrow passageway. And if you succeed 80% of the time, life is good, right? That's what answers like this might matter, right? They're not in environments where safety is critical, right? You're not going to just rely on an empirical decision there. So this is sort of how they look. We test with incredibly dense obstacles. Somebody asked me an obstacle density question earlier, and so we do fairly well. This is of course in our simulator. So maybe I'll just show you what it looks like in practice. In practice, we don't test with obstacles as dense as in the simulator, but we can fly pretty reliably, right? And this is running, cycling through at about 30 milliseconds, the control loop. We're running in like 7 kilobytes of memory, 20 odd neurons in the hidden layer, a very small policy running on each vehicle, including an attention mechanism that attends to obstacles that are static in the environment and 2 nearest neighbors. Works pretty well. This is sped up factor of 2.
So just a single layer.
Yeah, one hidden layer. One hidden layer. Yeah.
So what would happen if let's say, how do you converge to 20, for example, that you mentioned? Why not 10? Why not 100? And what is if you kind of did the, okay.
So we do a sweep over network architectures, right, is the answer. So there's a paper this year at ICRA on actually how do you find these networks that my student Shashank wrote. And so here what we do is this is a technique called hyper PPO. So you're trying to do 2 things. You're looking over the space of networks, and you're trying to simultaneously train these networks for the task I described. And so the question is, can you do RL for both? You can. You have to be a little bit careful. You have to somehow bring the network architecture on policy, right? So it has to somehow be in the same loop. And so it turns out you can do this. So the box at the bottom, U, is a network generator. And the graph of the network is concatenated with the state of the environment. And that's the system for which you learn a policy. Right? And you can do this. Right? You can do this very efficiently, as it turns out. Right? And you can find incredibly small networks. Incredibly small networks. Right? And by that, I mean something like this. So here's an example of a single quadrotor flying around. This is not the multi-quadrotor example. This is 4 neurons, right? 4 neurons in the hidden layer. This thing is told to describe a square. Now, this is not the full-blown problem that I spent the whole talk on. This is not navigating to a goal, along with obstacle avoidance, along with other moving things. It's just a single vehicle. There are no obstacles in the environment. But it is doing navigation to goal with 4 neurons in the hidden layer. Right? This was found using this hyper-PPO technique. Right? So now we have a systematic way of actually searching over network space and converging to networks that are really small in many cases, very, very small, right? And you can fly all kinds of things. You can make this thing fly other trajectories. You don't just have to fly a square and so on. But this is the extreme one that we really pushed, right? The flight with 4 neurons, right? So it's kind of remarkable that it runs on real hardware and is actually functional. So I think I'm very close to the end. So let me conclude. So it's kind of interesting that really small networks are quite effective for a task like this. Right? They're quite effective. Right? And if you want to accommodate small footprints, if you care about sort of real embedded processing, whether it's for speed or whether it's for privacy, or there might be many reasons why simply access to sending your data somewhere else is not allowed, then it may be valuable to learn sort of highly performant small networks, right? And you may get agile behavior out of such learned systems, right? There's some evidence that you get sort of behavior that you wouldn't normally generate through hand-programmed systems. So there's some flight modes in this case that you see that they're a little bit non-traditional. You can, in fact, in these kinds of settings, do zero-shot transfer. This is RL done in simulation, but you need a fast simulator that just simulates what you need. So the simulator does 2 things. It is exactly the inductive bias you need for learning this controller. That's one. And second is it has exactly this randomized collision model that generates post-collision states that are enough for you to learn recovery, right? Some guesswork went into doing each of these, but once you have that, and the simulator runs fast enough on a commodity computer in our lab, this thing trains in about 20 hours, right? So this is not some big cluster training far away. It's just, you can, on a daily basis, pick a new network and train on it. And now with our sort of this hyper-PPO technique, we can find small networks very quickly, right? So if you really have a size in mind, you can search up to that size and find the best network for your task concurrently with doing well at the task. We have a notion of what it means to do well. We sort of look at the reward collection behavior of each network. We sort of cut off at about 80% of the best one we find, and we admit all those. There's a bias search towards how you pick networks and so on. I didn't have time to talk about that today, but there's some interesting things. So RL has a charm for roboticists because it's been around for so long. Every few years it rears its head, and every few years roboticists get interested and excited by it. This is a little bit story for me as well, and I thought maybe that it could just have some value. It turns out that in certain settings, RL has a role to play in robotics. And for certain constrained settings, it may in fact be the way to go. So there's some really interesting things here. Somebody asked about papers earlier. These are the precursor papers, which sort of we were doing 7-8 years ago. The stuff I talked about is in these 3 papers, which is all deep RL swarm control. We have a new line of work on generating small learned control policies. In one slide, I just covered the first of these papers, but there's several more. We also learn now small policies for locomotion, for manipulation, for other tasks other than flight. But, unless you all think that I'm now a complete convert to deep learning and end-to-end systems, that's not entirely true. We have a new line of work on doing fast planning and replanning with no learning that has its own value. So if you're interested, take a look at our dream paper, which shows up at TRO, where we do highly dynamic environments, where we basically hurl obstacles at the vehicle at very high speeds, and the obstacle densities are significantly higher, and where we want to give some guarantees, not the type of work I described today, right? So that line of work is still continuing. I don't think I'm going to part with that anytime soon. So there's a few lines of work. So I'll stop here. Yeah, thanks very much for your time.
Thank you, Gaurav. There's a lot of excitement. So let's start question in the room, and I'll also monitor the online. Go ahead, Derek.
Yeah, really cool. I appreciate your remarks about comparing the learn control to sort of a traditional, I guess, or principal control design. With these really small models, it occurs to me that you could just about write them down mathematically and compare them to the traditional control. And I'm curious if you just sort of rediscovered a natural control design, like a artificial potential based approach or a Voronoi based approach in the learning. And if that were true, then like you suggested, you could start with a traditional model. I was particularly excited about your replay engine because thinking about, Tesla autopilots, it's those edge cases, it's the collisions that are so rare that there's just not enough data to learn. But maybe in those edge cases, the traditional approaches would fail because they have idealizations that suddenly are not valid. And so maybe a hybrid approach where you can learn by replaying all these edge cases to supplement the traditional control maybe would be the best of both worlds.
Yeah, I think.
Gaurav, can you just repeat the question for the online audience?
Yeah, so I think sort of two parts. The second part is, is there a more general lesson for the edge cases? Like, you look at self-driving cars, lots of edge cases for which you've never seen enough data or any data. So maybe sort of approaches that have randomized generation of these cases might be a useful way to go. We've thought about it a little bit, and that may well be true, because the sort of long tail of edge cases is a vexing problem for learned systems. Nobody quite knows how to do it. I agree with you. I think there might be some potential there. And then I guess your sort of earlier question about looking into these controllers to see whether their structures and code for either things we've already known in control for a while or maybe some other systematic synthesis of what's going on. We've just begun an investigation into an analysis of the latent that we learn, which then is decoded to generate actions. There's some emerging, so one thing you can very quickly see in that latent is that it separates safe states from unsafe states quite well. And that's not surprising because we get pretty decent collision avoiding behavior. But we haven't been able to look in the like with these 4 neurons in the hidden layer, it should be possible to write out what each one is doing. And we haven't quite got a crisp idea yet, but we're looking at it, sort of doing the tomography for these, right? Because that's the immediate first question that comes up, is that if you have a small enough network, you should be able to analytically say what it's doing. There are not that many functions at play. Yeah. But I don't have a crisp answer yet. We're looking. If somebody's interested, you can also have the code and the data for this are all available. So if somebody wants to poke at it, take it and sort of be interested to see what you find. Yeah. Other questions? Student question.
Yeah, in your hardware experiments, since you're having so many measurements, it's measurements of itself and also its neighbors.
Yeah.
I'm just curious, how do you account for latency in the measurements that goes to the motion capture and then comes back?
So the question for the online listeners is, do we account for measurement latency? And this is related to the broader question that Dinesh asked earlier. Measurements come with noise, they come with dropouts, they come with latency. We don't explicitly account for any of these. But when we implement on hardware, we're subject to all of them. And we seem to be robust to them, right? So that's a little bit of a two-phased answer. We don't model them explicitly. We don't do anything about them. And in fact, they're available perfectly in simulation. But it seems not to matter. Now, to some extent, we're beneficiaries of the fact that these vehicles have a good IMU on them. And the IMU measurements are made on board, and they're made at extremely low latency. And so they're also available on board. They're not sent somewhere and collected back. And so the self-state measurements are available locally, right? So, you get some wins as a result of that. But no, we don't model them explicitly.
Yeah, nice talk. Like one question I had was in the scaling law that you had shown for up to like 128 agents, right? It appeared like the models which were trained from scratch did perform well for the 128 agents.
Yeah.
But the slope for the graph until like 68 agents was actually higher than fine-tuning the model.
Yeah.
Is there like an reason why you would expect such a behavior?
Yeah. Yeah, I think I understand what you're. Let me see if I can find the picture again.
Slide 20.
Like this guy, right?
Yeah.
Yeah. So your question is sort of why is the blue line sort of above, right? One hypothesis is that as the blue line is sort of from scratch, and so it's not clear whether our estimates of the reward function, as we're training bigger and bigger networks from scratch, is as well done. One of the things is we hold for 1 billion steps. So we train for the 48.6 network, we train for 1 billion steps. What we really should do is also scale the training time for those bigger networks. Then probably we might get the blue line to be under the red line, but we didn't do that here.
That's
right? So there's this added constraint of holding, so you have the same amount of simulation time. Yeah, because in principle, you're right. If you're learning from scratch for a particular system, you should always be able to do better than all these other systems. And ultimately, you do.
Yeah.
I mean, it's not like it lasts forever. But even in the beginning, you could probably do better. Yeah.
Also, the fact potentially that you have no perception, right? So these scaling laws may be somewhat meaningless because of that in some sense.
Yeah, maybe. I mean,
your communication complexity is increasing.
Yeah.
As you scale up.
Yeah, though in these sort of these numbers are so small that it doesn't really matter, right? I mean, our experimental setup could easily handle 2-3 times these numbers with no appreciable impact on the latency.
Okay.
But the real impact on latency will come when you don't have, if I ask you the question, so great, so go fly in the wild and make neighbor observations. And what sensor am I going to carry on my vehicle that in an omnisphere around me can see 6 closest neighbors? I mean, such an idealized device doesn't exist. I would approximate it using some array of cameras and ranging, and it would be subject to the constraints that then Dinesh was asking about, which is half the time you're not going to see the second or the closest neighbor, or they're going to temporarily go behind something or miss them, or stuff like that. Another way to do it is the way you described, which is even in the wild, you do it by communication. So communication is, after all, sensing at a distance. So you make your measurements, I make my measurements, we share on some channel, but that channel will have dropouts and will have all kinds of other issues. One of the other things with communication is that things become aliased very quickly. So if I'm flying around and we agree to communicate and you tell me your location, well, when I look with my camera, it's not easy for me to know that you are the person who said I'm 3 feet away and not him, right? This aliasing problem is non-trivial. So in robotics, very often you cheat, and then the robots are color-coded, and the blue robot says blue is 3 meters from you. But then we're in the realm of really simplifying the problem too much. So yeah, those problems are very real.
So following question, I spent a lot of time working collision avoidance.
Yeah.
And if you do gaming and graphics, life was easy, right? And you also showed, your papers at the end, reinforcement learning, deep learning, and the old-fashioned way, trajectory. So when it comes to collision avoidance, we can do all those trajectory prediction, buffer boundary zones, MPC.
Yeah.
But again, when it comes to perception, we don't have a choice but deep learning.
Yeah, that's
at the
true.
moment.
That's true.
We're stuck with it.
Yeah.
And that deep learning, you did a lot of GPU, a lot of inferencing.
Yeah.
All the zero shot. So I believe still in all this autonomous system, perception is the biggest bottleneck, where the only known solution is deep learning with all the problem deep learning, which is expensive. How do we overcome that? That is the biggest challenge there for us.
Yeah. So one way is to Here, actually, the perception problem, it has all the problems you talked about, but it has one virtue, which is because the task only requires collision avoidance, I don't need to know that much about the entities in the environment, but I need good range measurements to them. And that is a narrower perception problem than the bigger vision problem, which is much harder. So maybe there's some hope that even if you have a deep learned technique to do that it can be relatively compact in size. That the networks you need don't have to be that big. Right? But I see where you're going. Like, what if the environment contains like the stuff you're doing? What if the environment contains grass? And what if the environment contains trees? And what if it contains leaves and buildings and people? And deep learning based perception gets big very quickly, and you don't have all the data you need. So I don't know. I don't know what the answer is for.
But one of the thing of that, you talk about biological system. We have murmuration of birds.
Yes.
We've seen honeybees.
Yes.
Okay. Imagine there are n number of bees, and could be 1,000.
Yeah.
But they're highly dynamic.
Yeah.
And they're doing collision avoidance.
Yes.
So it's an empty, no grass, but there are n number of bees or K
Yeah.
in his neighbor.
Yeah.
How are you doing it? I know Jan, you've done a lot of work on this problem.
These problems are most probably not solved through learning, basically. So you could do motion segmentation. You need to have lots of cameras sort of looking out.
Yeah.
And there are motion segmentation techniques that will find the moving thing and estimate its motion. And you can also find obstacles.
Yeah. Yeah.
Dr. Monzo, I want to pitch in a little bit. I was trying to discuss this with you later in our meeting, but the things we talked about is I think one of the solutions it could be like it's a new type of sensor. Maybe like a new type of sonar. You will sense what's happening around. Or it could be magnetic field that you're sensing around, what's been changing around. There is sensing it. I think it could be some new type of sensor that would be one of the solutions for this.
Yeah. Cool.
Yeah, the birds, they are sensitive to the magnetic field.
They are. Yeah.
And they use it when they do long distance navigation.
Yeah.
Okay. The no more questions. Thank you, Gaurav. You can see so much excitement.
Thank you. Yeah. Thanks a lot.